In this video, we're going to look at oxidation-reduction reactions. So what is an oxidation-reduction reaction? Well, these are also called redox reactions for short. And a redox reaction is a chemical reaction that involves the transfer of one or more electrons from one atom to another. The atom that loses electrons we say is oxidized. The atom that gains electrons we say is reduced. A good way to remember this is by remembering the phrase oil rig. Oil stands for oxidation, is the loss of electrons, and rig stands for reduction, is the gain of electrons. Let's take a look at a very simple redox reaction. Here we have elemental sodium, sodium metal. This is not an ion and it has a charge of 0. Here we have chlorine gas. This is a neutral molecule, and again we have a charge of 0 on that molecule. Over here we have sodium chloride. Sodium chloride is an ionic compound composed of a sodium cation, which has a +1 charge, and a chloride anion, which has a -1 charge. So if you look at each species, you can see that the sodium went from a 0 charge to a +1 charge. It lost an electron. So we would say that sodium was oxidized. Chlorine went from a 0 charge to a -1 charge. So it had to gain an electron. And so we say that the chlorine was reduced. So this is a very simple redox reaction. And you can see here that we had a transfer of electrons. But sometimes the chemical reactions are more complex and more difficult to recognize whether species are gaining or losing electrons. So how do we recognize redox reactions for more complex reactions? Well, we have to assign something called an oxidation number or oxidation state. An oxidation number is essentially, it's a way of keeping track or bookkeeping for electrons. It's a measure of how many valence electrons an atom owns when it's in a chemical compound compared to how many valence electrons it has when it's all by itself and neutral. So we assign an oxidation number to each atom in a chemical reaction, and then we look at the products and reactants and see if the atom's oxidation number changed. If the atom's oxidation number changed when it was in the reactant side versus the product side, then we know that that atom had to have gained or lost electrons, and we know that a redox reaction occurred. Furthermore, if an atom's oxidation number becomes more positive or less negative from the reactant side to the product side, then that atom is oxidized. Remember the sodium. The sodium went from a 0 to a +1 charge, and we'll see that's the same as the oxidation state. So it was oxidized. If an atom's oxidation number becomes more negative or less positive from the reactant side to the product side, then that atom is reduced. The chlorine's oxidation number, or in this case its charge, went from 0 to -1. So it was reduced. So in order to recognize a redox reaction, we have to assign oxidation numbers. So let's go over the rules that we need to know so that we can correctly assign oxidation numbers to atoms in a chemical reaction. The first rule is that an atom in its elemental state has an oxidation number of 0. So the elemental form of metals is simply Na, the uncharged form, NaFe. Most of your gases exist in the diatomic state when they're in their elemental form. Your noble gases like neon, argon, krypton, that is the elemental form of those. And then there's a few other ones like sulfur exists as S8. Here's a more complete list of some of the elemental forms of some atoms. So take a look at some of these and familiarize yourself with them. Our second rule is that if you have an ionic compound that's composed of monoatomic ions, then the oxidation number is the same as the charge. So here we have a sodium cation with a +1 charge. Its oxidation number is +1. Here we have chloride, which has a -1 charge, and its oxidation number is the same as the charge. So for ionic compounds that are composed of monoatomic ions, the oxidation number is the same as the charge on each of the ions. The third one deals with hydrogen and oxygen. Hydrogen's oxidation number is almost always +1, and oxygen's oxidation number is almost always -2. So 90% of the time that's the case. The only exception for hydrogen is either when it's in its elemental form, if you have, say, H2 all by itself, that would have an oxidation number of 0. But anytime hydrogen is part of a compound, it's going to have an oxidation number of +1. The only exception to that is when hydrogen is bonded to some metal cation. In that case, when hydrogen is bonded to some metal cation to form an ionic compound, its oxidation number is -1. Oxygen, as we said, is almost always a -2. The only exceptions, of course, is if you have oxygen O2 all by itself, not part of a chemical compound, then it's in its elemental form and its oxidation number is 0. But when oxygen is in a compound, its oxidation number will almost always be -2. The only exception to that is when you have a peroxide, something like this. But those are very rare. So 9 times out of 10, oxygen will have a -2 oxidation number. Our halogens, which are fluorine, chlorine, bromine, iodine, etc., those usually have an oxidation number of -1. The exception to that is when they're bonded to a more electronegative atom. So chlorine here is -1, and it usually is. Here's an exception though. Our chlorine is bonded to a more electronegative oxygen. In this case, the chlorine will have a +1 in this example. And our final rule, the sum of the oxidation numbers is 0 if the compound does not have a charge, and the sum of the oxidation numbers is equal to the net charge if the compound does have a charge. So for example, here we have H2SO3. This is a neutral compound. There's no charge here. So the sum of all these oxidation numbers has to add up to 0. We know that oxygen's almost always a -2, and hydrogen's almost always a +1. So what is the sulfur? Well, we have to use some calculations to figure that out. Our oxygen is -2, and we have 3 total. So we have -2 times 3 for all our oxygens. Of course, that's going to be a -6 for all 3 oxygens. Our hydrogen is +1, and we have 2 of those in this compound. So for the hydrogens, it's going to be a total of 2. So then we have our 2 plus x plus a -6, if I can write that neatly. 2 plus x plus -6 has to add up to the net charge, but this is a net charge of 0. So if we use some algebra here, we can calculate that the charge, or excuse me, the oxidation number, not the charge, on the sulfur is a +4. Over here we have a dichromate ion. We want to use the same strategy, but appreciate that our charges, or excuse me, again, our oxidation numbers have to add up to -2 because that's the net charge on that polyatomic ion. Oxygen we know is a -2, and we have 7 of those. So all of the oxygens will give us a total of a -14 for all the oxidation numbers. Our chromiums, we have 2 of those, and so we could say 2 times x, where x is the oxidation number for each chromium. So 2x plus -14, all of that has to add up to a -2 because that's the net charge. So if we solve for x, we get x is equal to +6. So the oxidation number for each chromium would be a +6. So be sure you have these rules written down, familiarize yourself with them, and then pause the video and see if you can determine the oxidation number for each atom in each of these compounds. So we want to determine the oxidation number for nitrogen and oxygen, magnesium and bromine, etc. in each of these compounds. Pause the video and give it a try. Okay, so let's take a look at our first one, NO2. We know that oxygen's a -2, and we have 2 of those. So we have a total of a -4 for all of our oxygens. This is a neutral compound, so all of the oxidation numbers have to add up to 0. So our nitrogen, let's call that X. So X plus -4 equals 0. X would be a plus 4. So we know oxygen's minus 2, and we can calculate that our nitrogen is a plus 4. For MgBr2, magnesium bromide, this is an ionic compound, and our rule tells us that for monoatomic ions, the charge and the oxidation number are the same thing. Magnesium has a plus 2 charge when it's an ion, so its oxidation number is plus 2. Bromide is a minus 1 ion, and it has a minus 1 oxidation number. Xenon, well, xenon's the elemental form of that noble gas, so its oxidation number is 0. And sulfate, SO42 minus. Oxygen is minus 2. We know that it's almost always minus 2. We have 4 of those, so that gives us a total of minus 8 for all of our oxygens. Our sulfur, what does it have to be? Remember that all the oxidation numbers have to add up, in this case, to a 2 minus, because that's the charge. So our sulfur would have to be a plus 6. And finally, nitric acid, HNO3. Our oxygens are minus 2, and we have 3 of those, so that's a total of minus 6. Our hydrogen's a plus 1. All of the oxidation numbers have to add up to 0, so the nitrogen must be a plus 5. So be sure you practice a few more of these. Be comfortable with determining oxidation numbers, and then once you are, watch the next video to show how we can use these oxidation numbers in the total chemical equations to determine which species is oxidized, reduced, and whether an oxidation reduction reaction occurs.